The skyline of Manhattan, New York. At its heart, the ever-evolving urban core, Hudson Yards. Situated here, the Shed and 15 Hudson Yards are more than just buildings. They are living structures that break down the boundaries between art and engineering. We will closely examine how these two buildings turn the impossible into reality, following their actual construction sequence. Today we focus on the Shed. The beginning of the Shed project was an unprecedented challenge. First, the foundation. The foundation work for the Shed's fixed structure was carried out first. The construction sequence of the Shed's foundation generally follows that of 15 Hudson Yards. First, 10-meter deep caissons are installed down to the Manhattan bedrock. Then, a pile cap is placed on top of the caissons to integrate multiple caissons into a unified structure. A small column is constructed on top of the pile cap, followed by the formation of a slab above it. Although the Shed and 15 Hudson Yards are physically connected, each building's foundation independently carries its own loads. For the foundation of 15 Hudson Yards, being a high-rise structure, caissons deeper and of larger diameter than those used for the Shed were employed. Moreover, tie beams were also installed to connect the foundations and effectively distribute the loads applied to each one. However, because the Shed is not a high-rise but an 8-story structure, relatively shorter and slimmer caissons were sufficient. Moreover, there was no need for tie beams. Here's a comparison of each building's caisson lengths and diameters. The caissons of 15 Hudson Yards were designed with lengths ranging from 18 to 24 meters and a diameter of a meter. The length of the Shed's caissons is 10 meters, and the diameter is a half meter. The Shed's foundation transfers the loads of its fixed portion, but it carries almost none of the loads from the Shed's shell. So, where are the shell's loads transferred? It is the platform. The shell portion of the Shed is a structure resting on the platform. Therefore, the rails that allow the shell to move are also built on the platform. Most of the shell's load, totaling approximately 4,000 tons, is transferred to the platform and then to its foundation. Consequently, the foundations of the platform and the fixed portion of the Shed are constructed independently. However, at this point, a single issue arose that dramatically increased the construction difficulty. It was Amtrak Tunnel that runs directly beneath the platform. This line is a high-speed passenger route connecting New York Penn Station with Albany and Niagara Falls. This tunnel is as far as about 20 meters from the Shed's foundation, but at its closest point, it is only around 10 meters away. Therefore, the Amtrak tunnel could not directly bear the loads of the Shed's approximately 4,000-ton shell and the weight of the platform itself. Accordingly, in cases where the loads had to be transferred directly above the Amtrak tunnel, they addressed this by using transfer girders. The transfer girders were installed with a gap about 250 millimeters from the tunnel crown, and the space between is filled with a compressible filler. The loads transmitted from the platform were transferred via columns to the transfer girders and then dispersed through the caissons installed on both sides. Thanks to this load distribution, the Amtrak tunnel was protected from the loads above. In the latter half of 2015, after the foundation platform was completed, construction of the Shed's superstructure began. The fixed 8-story main building was primarily composed of steel-braced frame, and by 2016, the steel structure had been actively erected. The steel frame fabrication for the Shed was primarily handled by Cimolai, an Italian company. The completed frames were transported by sea, arriving at the port of New York, and then delivered to the Manhattan construction site by land transport such as large trucks. The Shed's construction site was surrounded by high-rise buildings and located adjacent to the Highline Elevated Park, making road access and assembly space extremely limited. These logistical challenges at the site posed significant difficulties in transporting and assembling the steel components. Therefore, transportation was mostly carried out during nighttime hours when traffic was lighter. The delivered steel frames were assembled on site using heavy equipment such as large cranes. The construction process of each floor proceeded as follows. First, the steel frame consisting of columns and beams was erected. Then metal deck plates were installed over the steel beams. These deck plates serve as formwork during concrete pouring and after curing. They integrate with the steel structure to form a composite slab, enhancing structural rigidity. Finally, concrete is poured over the deck plates to form the structural floor slab. The construction duration per floor ranged from 50 to 60 days, significantly longer than the typical 2 to 4 day cycle per floor seen in high-rise buildings. This extended timeline was due to the shed's complex design, large-scale steel structure, and the precision engineering required to integrate wide column-free spaces with the movable shell. The steel structure and concrete work for the fixed building, which began at the end of 2015, continued for approximately 10 months until late 2016. From 2017, curtain wall and facade installation began on the fixed building's exterior, and by fall 2018, glass panels were installed across the entire 38th Street lobby, completing the building's open and inviting aesthetic. The most iconic feature of the shed is its 120-foot-tall retractable outer shell. This shell unfolds from its resting position atop of the main building and glides out over the adjacent plaza to create the Mech Court, a large, enclosed, and climate-controlled performance base. The shell's primary structural element is its exposed steel diagrate frame. The prefabricated diagrate frame was manufactured by Chimolai, the same firm responsible for the fixed building steel frame, and the assembled components were shipped to New York. On-site assembly of the movable shell began in 2017. The frames were assembled on-site, but transported into the Mech Court. Due to the limited space at the construction site, cranes were used to lift the frames, which were connected using bolted joints. The diagrate frame was completed in the spring of 2018, taking approximately 1 year. Starting in the summer of 2018, installation of the ETFE cushions on the movable shell progressed, continuously transforming the shed's exterior appearance. However, due to the material properties of ETFE, another set of challenges arose during installation. Before that, we should talk about why ETFE. The shed's movable shell is a massive steel structure, weighing approximately 4,000 tons. For this enormous shell to move smoothly, its cladding needed to be as lightweight as possible. If traditional glass cladding had been used, the sheer weight would have overloaded the structure and made mobility impossible. This was the point where ETFE emerged as the solution. ETFE, a Teflon-based fluoropolymer, weighs only 1/100th as much as glass, while offering thermal performance comparable to insulated glazing. It is also highly flexible, allowing it to absorb structural movement and withstand hurricane-force winds. Thanks to these properties, the shed was able to reduce steel usage by around 25% by adopting ETFE. The ETFE claddings of the shed consist of a total of 148 air-inflated cushion panels. While most are triple-layered, the 2 panels on the north side, subject to the greatest wind load, were designed with 4 layers for additional stiffness and load dispersion. Each cushion panel features a meticulously engineered multi-layer structure. The outermost layer is printed with a silver dot frit pattern to partially block solar transmission and reflect intense solar radiation. The middle layer is a semi-transparent white film with 29% opacity that scatters incoming light, providing soft natural lighting indoors and minimizing shadows. The innermost layer is made of a transparent material that allows maximum light transmission. This multi-layer combination optimizes indoor lighting conditions, reduces glare, UV rays, and heat gain, and at night creates a softly glowing exterior illuminated from within. Some ETFE panels are as long as 21 meters, making them among the largest ETFE panels ever produced. These ETFE cushion panels were manufactured in welded form by Vector Foiltech in Germany, then individually folded and wrapped in polyethylene film for shipment to New York. Upon arrival, the cushions were stored in protective frames to prevent scratches or deformation, and each component was tagged for easy assembly and handling. After the steel frames transported from Italy were installed on site, aluminum extrusions and plates were attached to them. These aluminum extrusions serve as connection points for the ETFE cushions. The ETFE panels were then attached one by one to the steel frame. Each panel was fixed onto an aluminum-based profile and sealed with a cap seal. During this process, air inlet tubes were also installed on each panel. Once the ETFE cushion panels were fully installed, they were inflated at a stable ambient temperature and weather condition. 4 air supply units installed on the shed's roof continuously monitor and regulate the internal pressure of all cushions. This system includes variable speed main fans and backup fans, which automatically activate in case of failure to restore air pressure. Each cushion maintains a positive internal pressure of approximately from 200 to 600 pascals, regulated in real time by pressure sensors and a PLC-based control system to adjust for weather changes. For example, pressure is temporarily reduced during wind gusts and increased during heavy snowfall to allow snow to slide off. The installation of the shed's ETFE cladding faced several unique challenges. The first was temperature sensitivity. ETFE can only be installed at temperatures above 40 degrees Fahrenheit. Below this threshold, the material becomes stiff and loses flexibility, increasing the risk of cracking or damage. The construction team avoided work during cold seasons or cold snaps, adjusting the schedule to proceed only on days when temperatures rose above 5 degrees Celsius. When necessary, temperature heaters or enclosures were used to locally increase the temperature in the work area. Next challenge was high winds. Strong winds blowing from the Hudson River made the ETFE installation even more difficult. Significant on-site coordination and adjustments were required to ensure the panels did not become overly taut or slack due to wind, while also accounting for expected movement of the structural steel. Air inflation was carried out on relatively calm days to carefully prevent the film from fluttering or experiencing excessive stress during the process. The ETFE cladding of the shed is a core element that brought an architectural vision to life. Born from a fusion of material science, precise engineering design, and the on-site team's relentless collaboration and innovative problem-solving, this facade stands as a living proof of what moving architecture can achieve. Embodying lightness, flexibility, and sustainability, the shed's ETFE shell points toward the future of architecture and continues to inspire us all. The detailed construction process of 15 Hudson Yards will be continued next week. Thank you.